Hi, my name is Ferhat. I'm going to talk about reverse engineering of quantum circuits from power side-channel attacks. It's a joint work between me, my colleague Tranchi Su, and my advisors Rusika Piskac and Jakub Sefer. Let's dive in. The interest in quantum computing has grown rapidly in recent years, and its trend is similar to early stages of Moore's law. And with it grows the importance of securing quantum circuits, especially as these powerful devices begin to be deployed on cloud platforms like IBM Quantum, Microsoft Azure, and Amazon Braket. The intellectual property embedded in quantum programs can be highly sensitive when they are deployed to these cloud machines. While quantum computers offer unique capabilities such as the inability to clone quantum states, making direct information theft more challenging, but they are still vulnerable. The control equipment used to operate quantum systems present potential points of attack, and this area hasn't been thoroughly explored from a security standpoint. Additionally, the physical size of quantum systems makes them more susceptible to physical probing. This figure shows the operation of today's cloud-based quantum computers. Remote users submit jobs to the cloud provider, where the job management or similar server dispatches the jobs to particular quantum computers, also called backends on IBM Quantum. Typically, the digital instructions are sent to controller logic by such as microwave electronics, which generate the actual analog control signals sent to the quantum computer. Our trade model assumes that an attacker can access and collect side channel information from the quantum controller. This is crucial because through side channels like power consumption, we show in this work an attacker can recover control passes and from there reverse engineer the user's quantum program. This model highlights how an attacker can reconstruct the entire quantum circuit, gaining insight into the computations being run on the quantum device, right? The core of these side-channel attacks revolves around the recovery of control pulses, which is typically generated by arbitrary waveform generators, AWGs. An attacker can potentially recover the quantum circuit being executed, and I am going to tell how this can be performed by solving a combinatorial optimization problem. Let's first look at how quantum compilation happens. Similar to classical computing, quantum circuits typically consist of complex instructions. The preparation, compilation, and assembly processes used for classical computing programs are analogous to the activities needed to convert quantum circuits into low-level and hardware-specific instructions before they can actually be executed on quantum computers. Input circuit in the figure, a Qiskit quantum program, this can be as well an open QASM program, is translated into a gate level circuit. The gate level circuit is then transpiled in that involves breaking down non-native quantum gates into groups of native gates, mapping the logic qubits in the original circuits to the physical qubits on the specified quantum computers. Then the transpiled circuit is mapped to a pulse level circuit, which contains information in microwave pulses to regulate and control qubits in the quantum machine. This is also called scheduling. The top figure shows one example quantum circuit. It's a quantum adder, 4 qubits quantum adder, and the bottom figure shows one output circuit after transpilation. All the gates are transformed into native gates on this specific machine, and some operations are added to satisfy the topology of the quantum device. The gates on this figure are RZ, X, SX, and CNOT gates, as you can see. Now, let's look into attacker's measurement capabilities. Each quantum program, that's also quantum circuit, is executed multiple times, and each execution is called a shot. We assume the attacker can sample power traces from shots of a circuit, or they can measure a number of shots, and it is easier to divide this into individual shots since all shots perform the same operation. Here, single shot, in our case, in our attacker's measurement capabilities, single shot per channel power side channel measurement on the left assumes a stronger attacker model, in which the attacker is able to collect per channel power traces, whereas a weaker attacker could collect a single total power trace over all channels, which can be seen on the right, but not distinguish the power traces of each channel. And the rest of my talk will focus on total power trace attacks. You can find the details for per channel attacker in the paper. And additionally, our previous CCS work has researched the per channel power traces as well as the timing attacks. However, we did not solve the total power trace attacks. In this work, I am going to provide you all details how we can use the total power traces to reconstruct the victim circuit, which requires algebraic reconstruction, which requires solving an optimization, combinatorial optimization problem. Figure shows example control pulses for the SX, X, and CX gates. You can see the frequency and phase together characterize a pulse. The duration, which indicates how long the pulse is, amplitude, which indicates how strong the pulse is, and other parameters which determine the pulse's structure, such as which channels they are sent. All native gates on IBM Quantum have predetermined pulses. Here you can see an example victim circuit that is transpiled on 5-qubit IBM Lima machine. The goal is to recover the circuit from its power traces by finding the set of most suitable pulse level instructions that make up the circuit with minimum error. Okay, the starting time step here on the table, you can see the start of each pulse level instruction are given. If the attacker obtains this information, they can reconstruct the circuit, as the order of the instructions is enough to compile the same circuit again. The third column shows a complete quantum program written in Python that is actually used to generate the circuit on the left. While the per channel attacker aims to recover this table from the measured waveform from each derived channel, the total power trace attacker employs only a single mixed superimposed summed up amplitude samples due to the fact that the attacker does not have access to the individual derived channels. As seen from this figure, the first waveform on the left, on the derived channel on the up, D1 of CX is in the bottom, exactly the same pulse as in SX on the top. So when the pulses are summed up, such as on the right, it is not easy to distinguish them. First, we approach this problem by formalizing the circuit reconstruction problem. For specific quantum machines, we have priors about their pulse characteristic that map to native gates, as I mentioned. For each machine, however, these native gates and their pulse library can differ. Starting from a quantum device D, we specify the set of basis gates, model the set of drive and control channels, capture their channel information as labels, characterize a basis pulse on a channel C. A basis pulse may include pulses on several channels, such as CX gates. They all constitute a basis pulse library. Using the previous set of sets and function definitions, we can specify a pulse level circuit, represents a per channel power trace, also represents a total power trace, which is directly the summation of per channel power traces. We can encode the channel constraints which means there can only be at most one pulse on each channel at a given time step. This is going to be important when we encode the problem from a given trace. The goal of per channel attacker is to find the circuit from the set of all circuits that minimizes the distance between the total power trace of this circuit and the measured per channel power trace. Similarly, for total power attacker, we want to minimize the power trace of this circuit and the measured total power trace. We can model this problem in linear mixed integer real arithmetic, which is a first order theory that we can solve its instances using an off-the-shelf satisfiable modular theory solver such as Z3. Lyra is a powerful formalism that combines linear equalities and inequalities with arbitrary Boolean connectors and allows us to mix integer and real variables. This makes it highly convenient for modeling our complex reconstruction problem. However, current SMT solvers lack support for optimization problems. It's also worth noting that while SMT solvers can solve the decision variant of the MILP problem, their performance is not as competitive as dedicated MILP solvers. In fact, we couldn't find solutions for simple circuits using SMT solvers. On the other hand, we can effectively solve the problem using MILP solvers. However, MILP only accepts conjunction of linear constraints, and the problem specification needs to be convex. Therefore, we need to convert the linear mixed integer linear arithmetic constraints into MILP normal form without exploding the problem in our setting. In order to encode those constraints into MILP normal form and thereby to perform the side channel attack, we employed various linearization techniques from the operation research community. These techniques involve introducing additional binary variables and bounding them with so-called big M values to convexify non-convex problems that exhibit suitable patterns that I'm going to talk about momentarily. First, we picked a linearizable distance measure for our minimization objectives, which is sum of absolute differences, as our distance function. However, ABS function is not linear, thereby we cannot encode the objective function for an MILP solver. But we use a technique to encode ABS-based objective function in such a way that an equivalent feasible solution can be described by splitting the constraints into two, relaxing the original function into a collection of linear constraints. The logical conditions on binary variables can be also linearized. For instance, not as a function, not of a variable, x can be encoded as 1 minus x, or x1 or x2 can be encoded as their summation, which should be greater than or equal to 1, so on. We can also encode pseudo-Boolean constraints over binary decision variables, such as at most, at least, and exactly constraints by summing up the binary variables having a weight at most 1. In order to encode the channel constraints, we need to linearize the disjunctive constraints. There are two common methods for disjunctions, the big M formulation and the convex hull formulation. In our work, we used a big M formulation where a sufficiently large number M is used to nullify one set of constraints. This is accomplished by adding or subtracting the term M times 1 minus Y to the upper bound and the lower bound constraints respectively. The bounds are chosen such that they are as tight as possible. But we are able to statically over approximate M values in our problem setting, since the decision variable x's are binary variables that can take maximum 1, right? Here I will try to explain an important part of the MILP encoding over an example victim trace. The duration of the trace is 5 dt from dt0 to dt5. The victim runs their circuit on a hypothetical 2-qubit quantum device, D, having only two basis gates, X and SX. We simplify also the notion of label here, since X and SX gates have only one label and waveform. X gate on C1, SX gate on C1, and X gate on C2 are named as X1, SX1, and X2 respectively. The associated pulse waveform for gate SX1 is Gaussian, as you can see on the figure, having 4 sample points. There is another one having 3 sample points, and yet another having only 2 points. Binary decision variables encircled by blue rounded rectangles in the figure indicates all cases where a candidate gate is applied on the channel. For example, at time step dt0, a candidate gate x1 is applied on channel 1, and its pulse contributes to dt1 and dt2 since its pulse waveform has a duration of 3. The other possible cases where the gate can start at are dt1, dt2, and dt3. You can see some other constraints on the sketch, including pseudo-Boolean constraints. For example, there can only be at most one pulse on each channel at a given time step. The objective function is encoded in such a way that it minimizes the error between the victim's power sample, which are black dots at the bottom in the figure you can see, and the goal is to minimize the obsolete error, right? SAD, as I explained before. In our evaluation, we use 3 different IBM quantum computer: T-shape, L-shape, and H-shape. For quantum circuits tested, we use well-known benchmarks from QASM benchmark suite. The results of our evaluation on benchmark quantum circuits provide compelling evidence of the high accuracy and effectiveness of our techniques in reconstructing quantum circuits. The table shows that we are able to recover all the X, SX, and CX gates from all the benchmarks tested. It's important to note that while our techniques demonstrate high accuracy in reconstructing circuits from power traces, the resulting circuits may not be exact replica of the original circuit, but rather a semantically equal one, due to the transpilation procedure I explained in the beginning. This is analogous to the classical compiler optimization, where reverse engineering from binary code to the original C code may not yield an exact reconstruction. Thank you. For future research and developments, we aim to investigate defense techniques in order to enhance the security of quantum programs in quantum computing environments. Thank you.